Today I'm going to present this paper called HIDE-ME, Enabling Location Privacy in Heterogeneous Vehicular Networks. This is joint work with Tobias Moiser, Oluwasegun Taiwo Ojo, Daniel Biskov, Ioannis Stavrakakis, and Ralph Steinmetz. The topic of this paper has to do with vehicles that want to be aware of their environment and be aware of events that may happen in that environment. For that, they can access their local sensors and obtain data from the local environment. But at the same time, it will be convenient for them to also have access to remote data, in order to take early actions in the case of there are accidents, traffic jams, or similar. In order to have access to this remote data, it requires that they put in place some system that provides access to this remote data is deployed. This data that is going to be, floating over the whole map of vehicles, or the whole cloud of vehicles, is what we call a floating car data system, and the data that is transferred from these vehicles is what we call floating car data, or FCD. In this paper, in this presentation, I'm going to assume that this FCD system is obtained by using locally, every vehicle is using locally their sensors to obtain local data and upload the data to a server, for instance, using a cellular network. Then the vehicles in this system report their location to the server, and the server sends to them the data, the FCD, that is relevant to them given their location and given the type of request that they are doing using this cellular network. For instance, in this example, the vehicle in the right has detected some event. It could be a traffic jam, it could be an accident. It reports it to the server on the top, and the server is the one that sends that message, that piece of data, to the vehicles on the left before they arrive, so they are aware that there's some obstacle or some issue happening in front, and that data can also be sent to other vehicles in the network. In general, we're going to assume that these messages, this data, may have different impact levels. So, for instance, different the message reporting an accident, a message reporting a jam, or a message reporting a street bump. We're going to assume that in addition to the location data, a vehicle reports to the server or requests to the server a certain impact level, declaring what level of data it is interested on. Then what the server is going to do to select and send the FCD to a given vehicle is to identify whether the data to be sent is relevant to the vehicle given its location, and it has the appropriate impact level as requested by the vehicle. In this example, the vehicles, and there are three different levels, but the vehicles are only requesting the highest level of FCD, which is reported to them from the server. Vehicles, or people in general, are becoming more privacy aware, privacy sensitive. So what may happen is that vehicles may not trust or may not fully trust the server, and they may not want to share their exact location with the server. In order to do that, one technique that is very often used is obfuscation. What the vehicle does is, instead of providing the server with the exact location, what they do is they provide a circular presence area. So the server knows that the vehicle is inside that area, but it doesn't know exactly where. The problem with that is that since the server doesn't know exactly where the vehicle is in the area, it may send messages to the vehicle that are not relevant to it, just because the location or for which that message is relevant is inside the area, but is not where the vehicle is. On the other hand, if the bandwidth, that the server can use to report or to send the FCD to a vehicle is limited, it has to select which data to send, and the average impact level of the data that is received and used by the vehicle is reduced. In this example, on the left, without any obfuscation, the blue message is going to be sent only to the two vehicles that are in the appropriate location, and because the location is completely known. However, if vehicles on the right, if they start using obfuscation, then this vehicle here is announcing an area that overlaps with the area for which this message is relevant, and therefore is going to be sent this particular message. That message is really not useful for the corresponding vehicle, but that is not something that the server can know, and therefore it cannot avoid sending that message. In order to compensate or a little bit for this problem with obfuscation, we're going to assume in this work that vehicles cooperate. So in addition to downloading data directly from the server, we're going to assume that vehicles that are close to each other, that are in range with each other, they can exchange using some low range communication technology, like Wi-Fi. They can exchange the data that they receive from the server. And essentially, since this is close range communication, we're going to assume that there's no limitation in bandwidth. So this vehicle-to-vehicle communication and cooperation may be used to compensate for the loss due to obfuscation and to better use all the communication capabilities of the different vehicles. The problem with this is that if we want to really use all these resources, we have to provide some level of coordination. Otherwise, they will all request from the server the highest impact level messages, and then they will end up having the same data. So no new data will be obtained by exchanging the messages that they receive from the server among each other. So one way to coordinate, one classical way to coordinate, is to have clusters of vehicles, and in each cluster to choose a cluster head. So that cluster head is going to use all the available bandwidth, all the available downlink bandwidth from the server. So it's going to aggregate all the available bandwidth from all the vehicles in the cluster. It's going to receive as many FCD messages as possible, and then it's going to distribute this data to the other vehicles. The problem with this solution is that it's fully centralized. That means that the cluster head is a single point of failure, and in particular we're talking about entities that move. So if the cluster head moves away from the other vehicles, then everybody in the cluster needs to realize this situation, and the cluster needs to be recreated. A new cluster has to be elected. So this requires strong coordination, because there is, there have to be agreement that a new cluster head has to be elected, and then a leader election process must be started. The question is, can we get a more robust solution with having lighter coordination? For instance, if we have a cluster head, like in this scenario, we have a cluster with three vehicles, and the cluster head is the car in the middle, the good news is that this vehicle can aggregate all the bandwidth and receive all the messages that the server has to provide. Once these messages have been received, the cluster head can distribute the messages to the other vehicles. Unfortunately, the problem is that if this cluster head disappears, no one receives anything, and they have to start this election process. So what we propose, instead of having a cluster head, is to have a completely distributed system in which there's only a probabilistic coordination. So just to introduce some aspects in our model, let's assume that the time is slotted. Then in each time slot, every vehicle is going to request a certain set of impact levels, messages from a certain set of impact levels that they want to receive. Then, as before, we assume that there is a cluster with n vehicles, and they can talk. All of them can talk to each other. And in every slot, as I mentioned, a vehicle is going to request a set of impact levels, which is chosen from a vector of probabilities. So essentially, a given vehicle is going to have a vector P with probability P1 to Pn. P1 is the probability of requesting impact level 1, P2 is the probability of requesting impact level 2, Pm is the probability of requesting impact level M. With these probabilities, the idea is that different cars may have different vectors. In this particular case, as you see, the car on the right is requesting only high-level messages, while the one on the left is requesting from the two top levels, while the one in the center is requesting from the three levels, but with different probability distributions. Then the problem is that if we allow this whole range of possibilities, then we need to solve a problem in which optimization may be very hard, and it may be very complex. So what we're going to do is we're going to consider only one single strategy or one single vector of probabilities for every privacy level that cars may use. And privacy level essentially is given by the radius of the area that they declare to the server. So we're going to have a game in which each vehicle has a privacy level J. Each vehicle J has a privacy level V sub J, which is chosen from a discrete set and is going to essentially give or determine, what is the size of this area that it provides to the server. And by using this technique of obfuscation that we described before, as we said, this is going to require to increase the required bandwidth, because now more messages are going to be sent to a vehicle that has a given privacy level, because it's requesting all the messages that are relevant to a whole area instead of a given point. And at the same time, the average impact of the data the vehicle is receiving is going to be reduced. So we denote those two parameters as AVI and mu VI. AVI is the bandwidth that is going to be required by vehicle that uses privacy V to receive the messages with impact level I, while mu VI is the average impact per bit that this same vehicle is going to receive from messages with impact level I. So the solution to this game is going to be a vector of probabilities, essentially a vector of strategies, one per privacy level. So PV is going to be the mixed strategy of a vehicle whose privacy level is V. As you see, we're going to have all vehicles with the same privacy level using exactly the same mixed strategy. whatever the solution, it needs to satisfy the bandwidth restriction, because as we're going to assume that the bandwidth of messages that a given vehicle can receive from the server is limited by this capital A in bits per second or bits per slot. So the expected bandwidth of a given given a strategy PV has to be limited by this value A, independently on which privacy level is chosen, this privacy level Vj. So for a given privacy level V and for a given I, this is the amount of bandwidth required, and this is the amount of bandwidth required by aggregating overall impact levels. And what we want to do is we want to maximize the utility. So for a given privacy level V, this would be the utility, expected utility for a given vehicle that is using that privacy level. This factor on the right is the probability that that vehicle receives all the messages of impact level I, while this part here is the utility, which is the average impact per bit times the number of bits, the utility that is going to extract if those messages are received. So summing over all the impact levels, we get the utility of a vehicle using privacy level V. And as we said, the solution of this game will be a set of strategies PV that respect these bandwidth requirements and maximize the utility of vehicles. In particular, I'm not going to go into the details, but we are able to propose a procedure to obtain such a solution, which, as I said, is a set of vectors PV for the game. The process to find the solution involves, calculus and an iterative process. And what we can show is that this solution has very nice properties. In particular, it's a mixed Nash equilibrium. Well, it's mixed because it's what we're giving is a vector of probabilities, and it is optimal. So it maximizes the overall utility. Unfortunately, it's a Nash equilibrium, but we don't guarantee that it's the only Nash equilibrium. And it is optimal, but we cannot guarantee that it's the only optimal solution. That means that if we want this solution, the solution we find, to be used, we must rely on all vehicles computing it and deploying it in a coordinated way. So it's a very light coordination because they can compute it in a distributed way and they can deploy it in a distributed way, but they need to agree that they're going to use this solution in order to achieve an optimal utility. So just to give an example, if we have two impact levels, one extreme strategy would be to only send or only request high impact messages, but then we will be losing, all the low impact messages that we could achieve or we could obtain by, indirectly requesting, if we coordinate somehow, as I said, probabilistically, if we coordinate and instead of all of us requesting high impact messages, some of us may impact lower impact messages. If on the other hand we go and we all request low impact messages, then the loss that we have is even higher because we don't get any high impact message. So the solution is somewhere in the middle, in which probabilistically we request low impact messages and high impact messages with certain probabilities, and we show that in this particular case I'm implicitly assuming that there is only one privacy level. But if we all use the same distribution of probabilities, what we get is an as equilibrium in which no one is going to increase its utility by changing this distribution or this probability, the probability we're using. We have used our solution and tested it. We have implemented it and tested it in an evaluation platform, which is a simulator that combines a simulator of the communication and a simulator of the vehicle's movement. So we use this platform called VEHICLE.KOM that has been developed in TU Darmstadt. That combines Simonstrator, which is a simulator of the wireless communication aspects, and Sumo, which is a simulator for the movement of vehicles, and has embedded a map of Cologne, so you can do experiments in a realistic urban environment. We assume that we have an area of 200 by 200 square kilometers, in which we are going to look only at a cluster of vehicles that is placed in an area of 2 by 2 kilometers. And we are going to assume that we have 4 different impact levels in our messages, and each impact level has, the higher the impact level, the lower the probability of that particular event level happening, and the increase in the relevance. So probably the impact level of 1,000 is something that occurs very rarely. It could be a big, crash, and it may affect up to 100 kilometers around, because it could perturb the traffic of maybe a big highway. In general, we're going to assume that the bandwidth is limited, and by default, we're going to assume that the bandwidth is limited to only 100% of the bandwidth required. In particular, we're going to assume that 100 messages per slot are generated, and only 10 messages per slot can be received by a given vehicle. So this is, the appearance of this platform, in which you can describe the behavior of the server, you can describe the behavior of the vehicles, and you can introduce all the parameters of the simulation. And this is the map of Cologne that is used, where the square shows, the area in which our cluster of vehicles is placed. So we're going to compare 4 different approaches. The first one is the one we just described, in which we solve a system, or we solve an optimization problem in which we want to obtain this vector of probabilities per privacy level. We want to compare that with the trivial algorithm, in which there's no cooperation at all. So all vehicles just request the highest impact level. It's like a very greedy approach, greedy and naive approach. Then we're going to compare it with clustering with perfect failure detection. In this case, this is going to be our kind of gold standard. This is what we like to have, because essentially clustering is the best you can do. You have all the available bandwidth is aggregated and is used to download all the messages to one particular vehicle, that then distributes it using the vehicle-to-vehicle communication. The fact that it has perfect failure detection and immediate election of a new cluster head makes it the perfect, of course, not achievable situation. It's impossible to, in a real deployment, to have this level of functionality, this performance. But it will be a reference for us. The closer we get to the performance of the GK, the better. Finally, a more realistic clustering is assuming that the clustering doesn't have perfect failure detection. So the detection of the cluster head leaving the area, this 2 by 2 area that we are assuming, is detected using some timeouts, and when that is done, then all the vehicles that are still in the area, they need to negotiate and elect a new cluster head, which again takes a little bit of time. So that means that this is a much more realistic technique, and it's probably a more fair comparison of the performance of our strategy. We're going to look at three main aspects. One is, what is the utility that we obtain with respect to the maximum possible utility, which is the utility that you would get if we get all the messages. Also, what is the bandwidth that is being used per vehicle? We have a limited bandwidth, but that limited bandwidth is in average. We have as I said, by default, it's going to be a 10% of the available of the required bandwidth. So we don't want, we're allowed to access this 10%, because what we want to have is on average this 10% bandwidth, but we don't want to go above that bandwidth too often. And then we're gonna see what is the resilience to having more or less privacy concerned vehicles. So we're gonna see what happens when all vehicles are reporting reliable locations, so they are not privacy concerned, how that degrades, how the performance degrades when more and more vehicles start being more worried about their privacy, and they increase their privacy level. So in these plots here, we compare the four goodness metrics when we play with the assigned bandwidth. So an assigned bandwidth of 10 is, as I said, is 10%. Every vehicle can only download in a slot 10% of all the available messages. And in this case, as can be seen, the naive strategy is the one that works the worst. The cluster approach without reliable failure detection, without immediate failure detection, it doesn't do that bad, but it doesn't do that well, and especially has a very high variance. While our strategy, which is the blue one, and the cluster-based strategy with perfect failure detection perform quite well. As I said, only 10% of the required bandwidth is available. As we decrease the available bandwidth, we see that our strategy suffers with respect to the cluster, the perfect cluster strategy, but still better than the cluster strategy in which failure detection and leader election has to be done, and it is in any case better than the naive approach. And then when we go to 0.1 bandwidth, which is less than one message per time slot, well, the naive strategy disappears from the plot, and our strategy actually, our approach actually suffers quite a bit. Seems like it suffers much more than the cluster with timeout. So the fact that you need to detect when a cluster head disappears and re-elect the leader is not as painful when there is very low bandwidth, as in our case the fact that there is redundancy in the data that is downloaded. However, when we look at how we do with respect to the highest impact messages, as we can see, essentially independently on the assigned bandwidth, we get pretty much all the high impact messages under the three bandwidth restrictions, while the naive strategy doesn't get all of them. As you can see here, essentially the 0.1 assigned bandwidth doesn't allow a given vehicle to download directly all the high impact messages that occur. When we look at the bandwidth, what we see is that our strategy typically stays below 1, which is the bandwidth that is assigned to us on average, and certainly the median is always below. Only in this case is at the line, while the naive and the clustering with with timeouts, and even the clustering, the perfect clustering, there are many cases. Look at this, outlier bar here. In many cases, they exceed the available bandwidth. So in that sense, our approach is much more stable. Well, when we look at the impact of privacy, what we're showing in the x-axis in these two plots is the situation from having all vehicles providing the exact locations to having all vehicles being privacy aware with 10 kilometers of radius in the area that they declare to the server. And as we can see, the clustering with perfect detection is quite okay. The utility only goes down from 95% with respect to the optimal utility or to the maximum utility to 93. In our case, we stay right there. We are very close to what the GK is doing, while the clustering with timeouts is doing worse. It's always below 90%, and the naive approach goes all the way down to 83%, to 83%. If we look at the impact levels that are not at the top, not at the lowest level, what we see is that we are able to preserve and get messages from this impact level even with almost 70% of the vehicles being privacy aware. It is interesting that the naive approach doesn't get any of these messages at all. So just to conclude, what we have shown is that using achieving privacy via obfuscation can be combined with this V2V cooperation with probabilistic coordination to achieve a performance that is comparable to scenarios with no privacy, or scenarios in which you have a perfect coordination via clusters. What we show is that no strong coordination is required, but we rely on all vehicles computing a solution which is in a equilibrium and adopting it. So what we would like to do in the future work is to see whether we can find a solution using a much simpler process, because the algorithm to find the optimal solution that we have now is quite involved. I invite you to see the details in the paper. And we would like to have this optimal solution to be a single Nash equilibrium, so all the vehicles have an incentive to go and use exactly that particular solution. Thank you very much for your attention, and if you have any questions or comments, please just email me or email any of the authors, and we will be very glad to answer your question.